This is a free response question from the year 2002, number 3. When you take the AP Physics C Mechanics AP test, there are 3 free response questions, so this was the 3rd this year. It's not super likely that you would find one that was all about a potential energy curve, but it could happen. It did happen in 2002, and there's a couple others out there. So let's see. This was a hard question. The year that this happened, this predates me teaching physics by many years. The year that this happened, I happen to know, because you can look up the average scores, this one was, it didn't go super great for students. And I think the reason is that this knowledge that we're really focused on right now, that about total mechanical energy being conserved, and that the derivative of this is the opposite of force. That's a little corner of physics that gets kind of dusty, if you know what I mean. Like, we don't really revisit this that often. So, you know, it is what it is, I guess. But now, this is front and center, so I don't think this should be too hard for us. So here's our potential energy curve. On the axis below, sketch the graph of this. Now, of course, anybody should be able to do that. So when you plug in x equals 0, you get 2. When you plug in x equals 1, you get 4/3. When in doubt, just make your point bigger, so it's got to cover up the right value. When x is 2, and this is 1. When x is 3, it's 4/5, which is 0.8. When x is 4, that's 2/3. And when x is 5, it's 4/7, which is, I don't know, probably about there. Okay? And they want you to sketch the graph of this, so not just the points. Now, you know what kind of graph this is. This is an inverse function, right? It's basically a version of the 1 over x, like tweaked around a little bit. So it certainly would not be like jaunty, like just connecting these things in straight lines. They're saying sketch, so, you know, doesn't have to be perfect. What they're looking for, I would have to go back and look at the scoring guide, but I think they want that it's decreasing, that it goes through like at least some of the right points. You might be allowed to make like one mistake plotting, and that it's decreasing in concave up. And they specifically use that kind of language in the scoring guide. So they know that we're also studying calculus, so no secrets about that. Okay, so that looks good. Determine the force associated with the potential energy function given above. Okay, so the force is equal to negative derivative, and so let's see, that's negative derivative of, what is it, 4 over 2 plus x. What's the derivative of that? That's maybe better to write for calculus friendliness like that. So that's equal to the negative sign. This is a power rule, so that's 4 times 2 plus x to the negative 2 times the derivative of what's inside is just 1. So it's 4 over 2 plus x squared. And oh, that's it. So that's our answer. So I thought maybe they asked for it at some particular location. So that's the force. I think that they gave you maybe like 2 out of 3 points or something, all of them except for 1 point if you blew the negative sign there. But we do have to flip the sign of that. Okay, so how about part C? Suppose that the object is released from rest at the origin. Determine the speed of the particle at x equals 2 meters. Okay, so at the origin and at x equals 2 meters, the total mechanical energy is the same for both, right? So at the origin, we've got, let's kinetic, how about if we just write this equation first? So kinetic energy plus potential energy at the origin has to equal kinetic energy plus potential energy at position 2, because mechanical energy is conserved. So I think they told us that it's being released from rest, so that's 0, plus the potential energy at 0 is 2. So the total mechanical energy is 2. The kinetic energy here, I think that's what we need. We want 1/2, what's the mass of this thing? Half a kilo. 1/2 mv, the velocity at position 2 squared, plus the potential energy at 2 is 1. So that looks like, let's say the velocity is going to be 2, I think. Let's just do the math to make sure. So we move the 1 over here, then we multiply by 2, and then we divide by half. Oh, these, yeah, so the velocity at 2 is going to be 2 meters per second. So if you're wondering, like, hey, aren't you like a big show your work guy, McGrath? No, not really. You just need to show your thinking. So, like, I don't care. If you go from here to here, I don't need to see that. That is, like, below your pay grade, below my pay grade. You want to do that in your head? And that's fine. But this is totally different here. Like, this is communicating to somebody what you are thinking. This, like, if you want to show more steps in between here and here, that's fine, but that's like showing them a level of detail that's really not necessary to show somebody that you know what you're doing, right? So there's way more points assigned to this than here. You make a little algebra mistake, that's, you know, your administrative assistant probably would have caught that in the real world, so less important. All right, in the laboratory, you are given a glider of mass 5 kilograms on an air track. So that's basically like, you know, low friction cart kind of situation. And we saw those dry ice pucks too. So same idea. On an air track just means that we can pretty ignore friction, and maybe they'll ask a question that has to do with friction about error or something like that, but we can ignore friction. The glider is acted on by the force determined in Part B. Your goal is to determine experimentally the validity of your theoretical calculation in Part C. So, in other words, we want to see if this is correct. So we think the speed is going to be 2 meters per second based on math. And what about the actual experiment, the real world? Is it going to be equal to that? So from the list below, select additional equipment you will need from the lab to do your experiment by checking the line next to each item. If you need more than one of an item, place the number you need on the line. And then in Part E, we want to outline the procedure, being explicit about what measurements you need to make in order to determine your speed. You may include a labeled diagram of your setup if it'll clarify your procedure. Okay, so basically what's going to happen here is there's some kind of thing. You could think of it, it's kind of like a spring, I guess, right? We're going to release this thing, and this is like, you know, if you could imagine it turning back up. This doesn't, but if you imagine it turning back up, then it might be like a spring with an equilibrium point over here. And we're only interested in going to 2, so that should be good enough for us, right? So the force here, it's a little stronger than it is at 2, but it's going to be accelerating in this direction. Now we need to know, we need some way of experimentally determining how fast it's going at 2. So how do you want to do that? Well, there's different ways you can do that. I will give you a couple of options here. I don't know if you are sure what a Photogate timer is. A Photogate timer, you want to see what one looks like? Hold on. Pull one out of this drawer here. Okay, that's not it. A Photogate timer looks like this. And you can, you hook it up to our little LabQuest mini thing and plug it into the computer. It's made by Vernier. Oh, look, it says Photogate on it, in case you didn't believe me. And inside here, I don't know how well you can see that. Probably not that well. There's a little hole right here where the tip of my pen is. And there's another little hole here. And inside those little holes, one end is the sending end of a little infrared signal, a little light, and the other end is a receiving end. And it basically functions like that. If you have, or you've ever been around an electric garage door opener where you just push the button and the garage door opens and closes, those things have a little safety feature so that, like, some little kid, if you like close the garage door and it's like coming down, if there's some little kid on its tricycle and it goes through there, we don't want the garage door to crush them, right? That would be bad. Or your dog or whatever. So there's a little beam at the bottom, and if something breaks that beam, then the garage door stops, and some of them turn around and it'll like open all the way again if that beam is broken. So this is the same idea. There's a little beam like that, and when that beam is broken, well, there's a signal, and we can do with that signal whatever we want. But the most common thing to do in first year kind of physics experiments with a Photogate is to use it to control a timer. So instead of having a stopwatch where we have to like clumsily go start and stop with our thumbs and have all sorts of reaction time and human error introduced there, we can start and stop the timer with a couple of these yokes. So if you didn't know what one of these was when you first did this problem, that's okay, but now you do. So, and notice that stopwatch is also a choice, but it's a little bit problematic for reasons we will discuss in a second. So here's an idea. What if we set up an experiment where we start timing right here at time 0, and then we end timing here? And we know that this thing has gone, we can measure how far it's gone, and we can measure 2 meters, right? And we can measure how much time it takes to do that, and then we can just do position over time, right? All good? No, not good, because that gives you the average velocity from 0 to 2. And we are interested in what is the actual velocity here. So what we need to do is we need to find like a much better approximation of the instantaneous velocity here. We don't have like a radar gun or something to find the exact velocity, but we do have these Photogates. So here's one option. One option would be, here's the track, here's the 0 meters, here's the 2 meters. Set up the Photogates here and here on a relatively small interval, position interval around that. It could be like plus minus 10 centimeters. That would be fine. You go plus or minus 5 centimeters, whatever. Those would be good approximations of the slope here. We could definitely use that. That's one way to do it. If you wanted to use the stopwatch, I think you could write a good procedure that would work fine and would get full credit if you did like 1 to 3. Why would you want to widen the interval here? Well, when you're timing, when we're actually controlling that time, we can't have something that happens super fast and expect to have any reasonable degree of accuracy there. So if you did want to use the stopwatch, I think you would just need to set up a larger interval, and the 1 to 3 would give you a decent approximation for the velocity at 2. You just have to make the case when you describe in your procedure that that's what you're doing. Let's see. You can look at, did you know that it's really easy to look up the scoring guides for these? If you type in 2002 AP Physics C Mechanics free response questions scoring guidelines, you probably won't even get all the way through. You know how your Google window will anticipate what you're looking for. It'll probably make a guess about what you're looking for there. And it'll take you to a PDF that is the actual scoring guidelines that the readers used to score this problem back in 2002. So I would encourage you to do that. We'll look at those more and more as the year goes on and we do more of these questions. So check that out and see what other options they gave and see how they scored that. So that's what I would do. I think I like best the meter stick to measure the interval, and 2 Photogate timers, 1 to start the time and 1 to stop the time. Right? You can't, I've had students in the past, this is probably my fault for not explaining well enough what a Photogate timer does. You can't say, use the Photogate timer to determine the velocity, to measure the velocity of the cart. Because that's not what a Photogate timer does. A Photogate timer, or a Photogate, just sends a signal when that little beam is broken. So it can start a timer and it can stop a timer, but it cannot just measure velocity. That's not what it does. So there you go. There's that problem.